Okay, number 5. A variable x follows a normal distribution with mean 2. Given that the probability that x is less than 3 is 0.8, find the values of these probabilities. Okay, what I want to do first of all is let me start with A, this 3 pieces of information, and see how I can be able to find a probability that x is greater than 3. What I'll do is I'll start by graphing, just doing a sketch of this of the normal curve. Now my mean here is 2, and then what I have is at x is equals to 3. Remember, this is x. So at x is equals to 3, the probability that x is less than 3, so cumulative probabilities that x is less than 3 is 0.8. So all this area is 0.8. All right. So if we want to find probability that x is greater than 3, so if we want to find the other area, which is basically this area here, if you want to find this area here, we know that the area under a normal curve is equals to 1. So basically this area will be equal to 1 minus 0.8, which is equals to 0.2. So that gives us the answer for A. Probability that x is greater than 3 will be equal to 0.2. And then B, probability that x is less than 1. So less than 1, first of all, what I need to do is to plug in 1. So in place of 1. So less than 1, it's basically this area here. It's this area. Now, by symmetry, that should also be equal to 0.2. So that will be equal to 0.2 by symmetry. Okay, and then part C, probability that x is between 1 and 3. Well, because the area under the curve is equals to 1, the area between 1 and 3 will just be equal to 1 minus 0.4, which will be equal to 0.6. Okay? So you can use a graph to basically find these probabilities. If you can remember the properties of a normal distribution function. Okay, I'm now moving on to standard normal distribution. So a standard normal distribution has mean of 0 and standard deviation of 1. So mean of 0 and standard deviation of 1. So basically what you have is a curve like this one here, and these guys that you see are highlighted here, these guys here, they are called z-scores, and they indicate how many standard deviations an x value is from the mean. Okay, so basically what's happening here is you have a normal curve, but it has been transformed to a standard normal distribution. When you transform that, the x value changed to z-scores, and the z-scores indicate how many standard deviations an x value is from the mean, and I'll show you that later on. So an x value can be transformed okay, into a z-score. So an x value uh, can be transformed into a z-score by using this formula. All right, so z-score is equals to the value. So the x value, this is the x value, minus the mean divided by the standard deviation. So here is an example. Um, so in this example, basically what we have on the left is a normal curve, a normal distribution, which has been transformed to a standard normal distribution. Now, what's happening here is the, let's start with the mean. The mean, of course, is 5 here, all right? But if you use this formula here, this is the formula that we're using. So if you use this formula, 5 minus the mean itself, so 5 minus 5, you end up with 0. And that's why you end up with a mean of 0 in the standard normal distribution, right? So that means that our new mean is 0 because 5 minus 5 is 0. Anyway, but if you look at a value like 6.2, so 6.2 minus 5 divided by 10, you get that. And that is our new z-score. So which means that the x value, 6.2, is 0.12 standard deviations from to the right of the mean. So basically what it means here is that that value, that 6.2, is basically our x value, which is 6.2 in this example, is 0.12 standard deviations to the right of the mean. Okay? Just to give you an idea of what's happening here, the relationship between x values and z-score. Remember, all those calculations are done using this formula here. This is the most important formula. Okay, so what you're saying that is that if each data value of a normally distributed random variable x is transformed into a z-score, the result will be a standard normal distribution. So or actually end up with a standard normal curve. So you have a normal curve, each x value is transformed, all right? What you end up with is a standard normal curve. Now, this is very important, especially when you're comparing two populations with different means and standard deviation. And this is how we write the distribution on a standard normal curve, all right? So we say Z follows normal distribution with the parameters 0 and 1, or you can say the Z distribution has mean 0 and standard deviation. Okay? So number 6, consider a random variable x which follows a normal distribution with parameters 2 and 3, and we need to calculate these probabilities. So one thing that you need to know is here we have z-scores and we also have x values. So what I'm going to do is for this probability here, this probability here, I'm going to use that distribution. But for this one here, I'll use Z distribution. So basically, standard normal curve. So I'll say Z normally distributed with parameters 0 and 1. All right. So this is for that, and this is for that. Okay, so let me start with A. Probability that x is less than or equal to 1. We can just use the calculator. So second, and then normal CDF. The lower bound is that, upper bound is 1, mean is 2, standard deviation is 3. Remember, these are the x values. So, and we'll end up with our answer as 0.369. How about the probability that z is less than or equal to negative a third? All right, so here we'll use the z distribution. Okay, here we used that distribution, so here we'll use the other distribution, the z distribution. So if you go onto your calculator, lower bound is that, upper bound is negative a third, mean is 0, standard deviation is 1. You'll end up with the same answer, right? So you'll end up with the same answer. So what you're saying is that here, 0.369. So this is a very important observation, which means that once you've transformed from a normal curve to a standardized normal distribution, from a normal curve to a standard normal curve, the areas under the curve do not change. So when you transform, basically, when you transform from normal curve to the standard normal curve, the area does not change. And that's why you have here equal areas, all right? They do not change. And that's why in these calculations you have the same areas once you transform. Because, well, if I transform 1 to z-score, so if I transform, right, to z-score, so z will be equal to 1 minus the mean, which is 2, divided by standard deviation is 3, which is negative a third. And that's basically what you have there. So, and once you've transformed that, when you find probabilities using the two distributions, the area under the curve remains the same. Very important. Anyway, I'll carry on to the next question. B. Calculate the probability that x is between 1 and 2. So here we are going to use the colors. So these are the x values. I'll just use the green for the x values. So if you go onto your calculator again, CDF, lower bound is negative 1, upper bound is 2, the mean is 2, standard deviation is 3, 0.341. And here, if you use z-scores, remember, z-scores, the mean is 0, standard deviation is, okay, so what's z-scores? Negative 1 to 0. The mean is 0, standard deviation is 1. You end up with the same answer. You end up with the same answer, which is 0.341. All right.